Hello. In this talk, I'm going to discuss recent work joint with Chuck Livingston about unknotting knots with a single full twist. This work is partially motivated by the following theorem of Oyama, which states that any knot can be unknotted with two full twists. The proof of this theorem is really nice, and I want to share it with you. Oyama bounces off of results of Yamamoto and Suzuki to begin with a diagram of the knot where locally all the crossings that need to be changed in order to realize the unknotting number all are located nearby and in this nice way, so that if you change this undercrossing to an overcrossing, you arrive at the unknot. Beginning with this picture on the left, Oyama twists these two strands up, this strand up and down on the ends, and recognizes this as a partial full twist to the left on U plus 1 strands, where U is the unknotting number of the knot. Grabbing these strands, if I do a positive or right-handed full twist on those strands, I arrive at this picture, where if I trace this rightmost strand, it will cross over everything at the beginning of that full twist, and then cross under for the remainder until it reaches this strand here. And so I see that I can pull it under and over here, getting something like this, which I can then pull down and over the rest of the full twist and get a picture like this, where this overcrossing is hovering above what looks exactly like a full twist on one fewer strands. I can undo that full twist by twisting to the left and get this picture, which is precisely the picture I began with, except that the undercrossings are now all an overcrossing. So looking at this theorem and this proof, you could ask many questions. You could ask, can I unknot a given knot with twists on different numbers of strands or with different signs? You could ask if every knot can be unknotted with two full twists, which can be unknotted with one full twist, and how, and that's the question that I want to discuss in this talk. So to make that a little more precise, when I ask if a knot can be unknotted with a single twist, or if I'm given a knot which I know can be unknotted with a single twist, I want to know, is that twist positive or negative, right-handed or left-handed? What's the linking number of that twist, and how many different ways can this happen? Just as an example, the trefoil can be unknotted with a single twist in 3 different ways. The first way is in this diagram. If I just grab these strands and do a left-handed twist, then it'll undo these 2 crossings and I'll be left with the unknot. Similar thing happens here. I grab these strands, twist to the left, and I'm left with the unknot. In this third picture, I grab these 2 strands, and if I do a positive twist on those strands, the result is to change that crossing. And so again, I have the unknot. Notice here that instead of listing the number of strands, I list the linking number. And here our convention for linking number is to orient this loop so that the linking number is non-negative. This gives rise to a definition. The set of unknotting twist indices of a knot we define by the following rule. A value L with a superscript of plus or minus is in the set of unknotting twist indices for K if and only if K can be unknotted with a full twist of linking number L, where the superscript tells me if that twist was positive or negative. For example, we just showed that the values 2 minus, 3 minus, and 0 plus are contained in the unknotting twist indices set for the trefoil. It turns out that those are the only 3 values in its set, but it is much harder to prove that there are only those 3 than it is to show that those 3 are contained in. Similarly, the figure 8 knot has these 4 values. It is a good exercise for those of you following along to take a diagram of the figure 8 knot and see if you can find those 4 twists. Similarly, that would only show this containment, but in fact those 2 are equal. And just so we have an example floating around, the torus knot T211 cannot be unknotted with a single full twist, and so its unknotting twist indices set is empty. And so looking at these three sets, you might ask, okay, in general, what does this set look like? And that leads me to one of the main results of our work, which is that given a knot K, there are two values m and n greater than 0, such that the unknotting indices set is a subset of a set of this form. Notice what this means. This means that I may be able to unknot K with twists of linking number 0 of either sign. But if I have non-zero linking number, then if it's a negative twist, I can have at most 2 and they're 1 apart. And if it's a positive twist, I can have at most 2 and they are 1 apart. And it turns out that if you have an unknotting twist indices set that has 6 values, that is exactly of this form, then those 6 values must be precisely these. I want to sort of sketch the proof of this theorem for you, and it begins with an observation. If a knot can be unknotted with a single twist of sign S and linking number L, which is non-zero, then negative SL squared surgery on K bounds a rational homology four-ball. And this gives us the ability to use tools like the Szabo Dehn invariant and others to examine this problem. Let me start with the first tool that we use, which is the Szabo Dehn invariant. The Szabo Dehn invariant associates to a rational homology 3-sphere Y and a spin C structure T on Y, a rational number Q. And Szabo and Szabo showed that if you have an integer surgery on K bounding a rational homology 4-ball, which is the case we would be in here, then if L is odd, you know that some of these D invariants will be 0. And if L is even, then you know some of these D invariants are 0 as well. So now we have a tool that we can apply to this problem. We can actually take this one step further and use the VI invariants defined by Ni and Wu. This is a sequence of invariants, which are non-negative integers. This sequence is non-increasing, and at each step decreases by at most 1. Eventually, this sequence will hit 0 and remain 0 for the remainder of the sequence. And there is a relationship given here between the VI invariants and the D invariants of this integer surgery. And because we know that some of those D invariants will be 0 if we're in this specific case that we are in, we can put restrictions on what the VI invariants are. In particular, if we consider that first index where the VI invariants reach 0, which is defined as the invariant nu plus, then we get this condition. If a knot K can be unknotted with a single negative twist of linking number L greater than 0, then L is in this range depending on that first place where the VI sequence is 0. And if you stare at this inequality long enough, you will realize that the gap between these two values is at most 2, and it's in fact only equal to 2 if the nu plus invariant is equal to 0. And because this is a strict inequality, that means that L can only take at most 2 values, and those 2 values are at most 1 apart. That gives me that for a negative twist, these are my only 2 options for some value of m. Because this theorem can't deal with L equal to 0, I have to allow for the possibility that at linking number 0, I could have a right-handed or left-handed twist that unknots the knot. The positives come from the following observation. I'll write as a fact. which is that if a value L plus or minus is in the set of unknotting twist indices for K, then the same twist but with opposite sign will unknot the mirror image of K. And that's not so hard to see, and in fact this is an if and only if statement. So if the knot K can be unknotted with a positive twist, then its negative can be unknotted with a negative twist, and its negative only has two possible values for the negative twist, which must be one apart. So we see that for a positive twist, they can also only be one apart. So that's how we show this theorem. There is a lot of work going on in the background there, but it has a nice application when you consider some nice families of knots, for example, alternating knots. So let me give you some background about alternating knots. It turns out that for each alternating knot, its VI invariants are equal to those of some T2N torus knot. And this comes from the fact that its Hegerfloor knot complex is also that of a T2N torus knot. And which T2N torus knot you choose is determined by the signature of your knot. Furthermore, the VI invariants of the 2N torus knots are really well understood. There's a formula for it. And if we use this in conjunction with this theorem, we can show that if I have an alternating knot, then that knot can be unknotted with a negative twist of linking number L greater than 0 only if L is one of these 5 values. And I've put an asterisk next to the 5 because it turns out that we can do one better. Linking number 5 is not realizable. But it turns out that these methods using the rational homology ball don't apply here. They don't rule this out. And so we need a new strategy. And so let me briefly discuss with you that new strategy. So let's start with another observation about surgery diagrams. If K can be unknotted with a negative twist of linking number L, then there is a knot J and an orientation preserving homeomorphism from L squared plus 1 surgery on K to negative L squared minus 1 surgery on J. And the basic idea of this is to start with this surgery and use that K can be unknotted with a negative twist of linking number L to do a blow up and then a blow down to arrive at a surgery diagram of this form. And through that homeomorphism, you can chase where the meridian of your knot goes and get a relationship between the D invariants of these two manifolds. And of course, we know from a relationship of two D invariants, we can get a relationship between the VI invariants. And if we're very careful about what that relationship looks like, we get a theorem of this form. So suppose again that our knot K can be unknotted with a negative twist of linking number L, and let's let N be L squared plus 1, just for notation, then there exists a knot J prime such that for the values of I between 0 and n over 2, I get this relationship between the VI invariance of K and the VI invariance of J prime. I want to point out a few things, although I'm not going to prove this theorem. The first thing I want to point out is that we've switched to J prime rather than J, and this is just because when we move to D invariance, we can change the sign of J and replace it with negative J in order to change this to an L squared plus 1. Okay. So really J prime is essentially negative J. Second, this notation here that you see throughout this relationship is just a formula that relates to what's in the brackets and this subscript, a non-negative integer. And this portion about whether L is even or odd is related to the set of spin C structures for the manifold. But given that you believe this particular theorem, we can show that an alternating knot K cannot be unknotted with a negative twist of linking number 5. Suppose, for contradiction, that K is an alternating knot which can be unknotted with a negative twist of linking number 5. Then in this theorem, N would be 26. And so we would have 0 to 13, so 14 different relationships between the VI invariance of K and the VI invariance of J prime. They would look something like this. There are two in particular that I want to point out to you, which is when I is 1 and when I is 6, the relationships look like this and this. In particular, they relate V8 of J prime and V9 of J prime to VI invariance of K. But recall what these VI invariants look like. They're a sequence which is non-increasing and decreases by at most 1. This gives us a relationship between V8 and V9 for J prime. And if we just do the substitution and rearrange, we determine that V1 of K and V6 of K have a difference which is between 1 and 2. So why is this useful? Well, we know K is alternating, so we know a lot about its VI invariance. In particular, Hegardt floor obstructions that led up to our main theorem force V0 of K to be 3 and V5 of K to be 1, knowing nothing about K other than it's alternating and the linking number is 5. This forces K to have the same VI invariance as the torus knot T213, again because it's alternating. But we know the VI invariance for this knot, and in particular, V1 is 3 and V6 is 0. And I claim we've reached a contradiction because the gap between those is certainly not between 1 and 2. So our results about alternating knots can be made a little bit stronger to say that you cannot achieve linking number 5. Using this and using our results related to some more classical invariants and Casson and Gordon invariants, which I haven't discussed here, but are in our paper, we can put restrictions, some pretty strict restrictions, on the signature function of our knot and on the ARF invariant of the knot. If I use these, then I can describe the unknotting indices sets for alternating knots, or at least what they could look like. So what we've showed is that depending on the signature of the knot, we get a different set of VI invariants because we're dealing with an alternating knot, and the unknotting twist indices set is a subset of this set here on the right. Notice something interesting, which is that as the signature gets large, the set shrinks, and in particular, it contains only values of 1. Down here, I noted that if L is odd, then we actually know exactly what the ARF invariant has to be in order for a 1 to be in its unknotting twist indices set. In particular, if K is an alternating knot and its signature is greater than 8 in magnitude and its ARF invariant is 1, then, well, neither of these 1s could be in its set, and so K cannot be unknotted with a single twist. So maybe I will leave us with just a few further questions. We have many more than these, but here are a few. We have done a census of prime knots with up to 8 crossings, and we have found that there are only 8 knots for which the unknotting twist indices set is completely known. In fact, the very first example with unknown values only has 5 crossings. It's the knot 5, 2. We know that these values are in its set because it has a knotting number 1, but there is a value, a positive twist of linking number 1, which could be in the set, but we don't know if it's realizable. And there are many more like this. We also would like to know if there's a non-trivial knot which realizes this full set. Of course, the unknot does, but are there any other examples? Okay. This would mean that the nu plus invariant would have to be 0, which would mean all the VI invariants have to be 0. And from our census of 8 crossing knots, current candidates at low crossings are the knots 8-3, 8-9, and 8-20, although we don't know if any of them realize this set. And finally, from our census and from working with these theorems, the case of linking number 1 is particularly challenging. And the reason this is challenging is because we'd be dealing with integer homology 3 spheres rather than rational homology spheres. This causes some issues with the way the theorems are structured, and in particular, the only theorem that we have that can really tackle linking number 1 is the one about arc invariant. Okay, so we really need some more work in order to tackle this particular linking number. And I think I will leave it at that. Thank you for tuning in, and thank you to the organizers for inviting me to give a talk. And I'm happy to answer any questions that you may have.